Hi guys. Since I'm not going to be able to be on campus tomorrow, I wanted to make sure we don't fall behind and post one of those video lectures. If you watched my video lectures on vectors, it's going to be very similar. Be just like one of my lectures in class, but on YouTube. Okay. So what I want to do today is recap what we did with potential energy, and then start talking about a new quantity that we call electric potential, which we saw hints of today in lab when we started talking about potential differences and voltages. So we'll see what that means later on. After this lecture, you should be golden for the remainder of your homework. You should be good to go. Again, it's due on Monday, so this homework and the last homework on Gauss's law are all fair game for your exam, which is this coming Tuesday. Okay. All right, so let's get started. Let's just review a little bit about what we did last time. Review on electric potential energy. So last time we started by talking about work, the work done in moving charges through electric fields. And we started by looking at the special case of a uniform electric field. So we had a situation where there were two oppositely charged plates. Oops, hard to draw. And there is an electric field in between them. And we had a point charge, a positive point charge, move from the positive to the negative. And we asked how much work was done by the electric field in moving this charge from the positive to the negative on that red dotted line. And with some calculus, we were able to show that the work done is just QE times the displacement over which that charge traverses in the electric field. Then we said, well, work is always minus the change in potential energy. So we get potential energy for free now that we know the work. Delta U, and I'm going to add in a UE here because it's electric potential energy. Delta UE, the change in potential energy from the positive plate to the negative plate is minus Q E delta X. So we had two results from just the uniform E field. Okay. By the way, this is the picture that I was mentioning in lab today. I said we redrew this picture in sort of 3 dimensions. So we had the negative plate here and the positive plate is at a higher electric potential energy. Okay. High potential energy. So that when that charge falls down this incline from high potential energy to a low potential energy, it goes through some change in electric potential energy, delta UE here. All right, so that was for the uniform electric field, and we did an example of a charge accelerating in a uniform electric field. I think that was example number 14 or something like that. Then we took a new case of point charges. We said that anytime a charge is inside an electric field, it is going to have some potential energy associated with it. So what if, the idea here was, what if a charge was not in a uniform field, but rather in the E field of another point charge? So the picture that we had was looked something like this. We had one charge that we called Q, and then we had another charge here that was Q naught, and they were separated by a distance r. And using that the same integral that we used to calculate the work done in the uniform case, right? We started with something that looked like this, f dot dr. But I won't go through all the steps, just to remind you. Using this integral, we were able to show that the work done in moving this Q naught from a distance, let's call this distance not r, but rather RA, to a new distance, which we called RB, that work was given by Q naught 1 over RA minus 1 over RB. Let me just make sure I remembered that correctly from last time. Yes. Okay. And again, we said that work is related to potential energy with this equation. And this is what allowed us to define the electric potential energy for 2 point charges for a pair of point charges. And this was UE is equal to Q naught Q over R. Okay. This is a big result. So remember, it tells you that the potential energy when these charges are separated by a certain distance that we're calling R is a shared quantity, right? Because while Q naught is certainly in the electric field of Q, Q is in also the electric field of Q naught at the same time. So they both have potential energies because they're both in electric fields produced by the other one. Okay. We also said that there was another way of interpreting this potential energy. We said that you might see it look like or be referred to as the work done in moving Q naught from infinitely far away to a distance r from Q. So they both mean the same thing. It's just you can see sort of two different. You can see it referred to two different ways. You could be asked, what is the potential energy associated with these two charges, or you could be asked, what is the work required to bring Q naught from infinitely far away to Q, and they mean the exact same thing. All right, so this is pretty much where we left off. I did mention at the end of class, what if you have multiple point charges? So let's revisit that, and we're going to do an example. So we took the case where we had just a random assortment of point charges here. Let's call this Q1, Q2, Q3, Q4. And we said, actually, let's get rid of Q4 because we don't need all of those. And we wanted to know what is the electric potential energy associated with this system. Of point charges. Now, what we did was we first looked at the distances between these. We call this R13, the distance between Q1 and Q3. This will be R12. This will be R23. Okay. Now, in order to figure this out, you have to remember, so we're looking at what is the potential energy of this entire thing. So you have to remember that the potential energy, electric potential energy, is a shared quantity among pairs of point charges. So you're going to have one potential energy shared between Q1 and Q2. You'll also have electric potential energy shared between 1 and 3, Q1 and Q3. You'll also have a potential energy shared between Q2 and Q3. And if you add those three up, you will get the total electric potential energy of the system. Okay? So you have to add up every pair of charges. You have to add up their electric potential energies. So this, just to be complete here, we have KQ1, Q2 all over R12 plus KQ1, Q3 over R13 plus KQ2, Q3 all over R23. Okay. Now, this does seem tedious because there are a number of terms, and if you add another point charge, the terms double. You get 6 that you have to actually calculate. But usually these things simplify quite a bit, and the big thing here is that you're not dealing with vectors. So you don't have to break anything up into components. Everything is a scalar quantity, right? We're dealing with energy. That's not a vector. All right, so before we move on to new lecture material, I want to do just an example. I think it's example 14 in your example sheet. Let me just check. Nope, it's problem number 13. So let's just start a new page here. Example number 13. Okay, this problem says that 4 charges are oriented on the corners of a square with sides of length A. If Q1 equals Q4, and they both equal 2Q, and Q2 equals Q3, and those two are minus 2Q, determine the electric potential energy associated with this group of charges. Also determine the electric... Okay, so there's one extra piece to this that we'll leave for later on, which says also determine the electric potential at the center of the square. So here's a picture. Let's see, I'll draw it over here. Okay, we've got a square, and we'll have Q1 down here, and we'll have Q. Let me make sure I'm drawing the right Q's here. Q1 is going to be in the upper left here. Q2 is in the upper right. Q3 is down in the lower left here. Q4 is here. Okay, each side of this square has a length A. And we're told in the problem that Q1 is equal to Q2. Oh, no, sorry. Q1 is equal to Q4. And they are 2 big Q. Okay, where big Q is just a constant. And Q2 is equal to Q3, and those are minus 2 big Q. Okay. So since we have 4 point charges, we're going to have, let's see, 1, 2, 3, 4, 5, 6 potential energies that we have to determine. Right? The total potential energy is going to be the potential energy shared between Q1 and Q2, between 1 and 3, between 1 and 4, between, let's see, 2 and 3, between 2 and 4, and finally between 3 and 4. So again, there's a lot of terms, but this will simplify greatly, and we're just dealing with numbers here. So let's figure out what all of these individual ones are. We'll start with U12. Okay, this is going to be K, Q1, Q2, all over R. The distance between Q1 and Q2. And actually, let's see. Oops. Let's just write it as A. The distance between Q1 and Q2. Okay. Now, we know what Q1 and Q2 are. Q1 is 2Q, and Q2 is minus 2Q. So if we plug those in here, we get K, 2Q, minus 2Q, all over A. And so just multiplying this all out, 4 minus 4, K, big Q squared, all over A. Now, potential energy can be negative. It can be both negative and positive. All right, keep going. U13, I'll take this a little faster. I'm not going to do out each step like I did in the first one. U13 is going to be KQ1, Q3 over A. But we have Q1 is 2Q, Q3 is minus 2Q, so we get the exact same minus 4KQ squared all over A. All right, U14, let's do that one. Here, Q1 and Q4 are both positive 2Q, so when we multiply it all out, we get positive 4KQ squared all over A. All right, halfway there. Let's do U23. So 23, we have a Q2 is minus 2Q, and so is Q3, so we get a positive again, 4KQ squared all over A. U24, those have opposite signs on the charges. Q2 is negative, Q4 is positive, so U24 is going to come in with a minus 4KQ squared all over A. And the last one, U34, same thing, minus 4KQ squared all over A. I noticed that I'm doing something pretty stupid. Hopefully you guys caught this before I did. So take a second to, if you haven't seen what I'm doing wrong, take a second to think about what I'm doing wrong. Okay. Let's zoom in and look at Q1 and Q4 first. Okay, so I'm claiming my U14 is wrong. All right. The reason that it's wrong is those things aren't separated by a distance of A. Right? So if we look at the square here, those are really separated by a distance of square root A squared plus A squared. Right? Because we have a right triangle here and a right triangle here of sides A and A. Okay. Well, the square root of A squared plus A squared is equal to the square root of 2A squared. Just combine the A squareds. And we can actually take the square root of both of those terms since it's a product underneath the square root. So we just get square root of 2 times A. Okay, so let's go back to U14. I'm going to erase, whoops, let's just rewrite that one. U14, was it positive? Yes, 4k q squared all over square root of 2 times A. And then the other one that's wrong would be U23, right? Because those are separated by that hypotenuse. So let's also erase U23. And that one was also positive, 4k q squared all over root 2 times A. All right. Now we're all set. We're ready to add these together and simplify. So, let's just plug everything into that top equation. We have U total is equal to U12 minus 4k q squared all over A, U13 minus 4k q squared all over A, U14 plus 4k q squared all over root 2A, U23 is plus 4k q squared all over root 2A, U24 minus 4k q squared all over A, and then U34 minus 4k q squared all over A. All right, looks messy, but we can simplify this greatly. Notice we have 4 terms that are all the same, and then these 2 terms are also the same. So we're going to combine those. We have minus 4, minus 4, minus 4, minus 4 kq squared over A, which will give us minus 16 kq squared, all over A. And then if we go back, we have plus 4kq squared plus 4kq squared, so it's going to be 8kq squared all over root 2A. All right, let's simplify this a little bit. Notice that there is an 8kq squared over A in both of these terms. Let's factor out 8kq squared all over A. Okay. If we were to factor it out of the first term, the minus 16kq squared over A, we should get just minus 2. And then if we factored it out of the second term on the right, we should just get 1 over root 2. Okay. So if you want, you can keep going with that, with the simplification, or I would be fine if you just figured out what minus 2 plus 1 over root 2 is. But I'm going to leave it there. We've basically whittled it down as far as it would go. Okay. All right. The last piece, what would the electric potential be at the center of the square? We're going to leave that for a little while and come back to it because we don't know what electric potential is yet. Okay. All right. So let's actually start working on electric potential a little bit. All right, so in order to see sort of how we define this new quantity called electric potential, I just want to take you back a little bit and remind you how we defined the electric field. Okay, with the electric field, if you remember, we defined it as, and this is a very important equation, and I know a lot of you don't have it memorized. Make sure you know this equation. It is very important. We defined the electric field E as being the force that a charge experiences divided by that charge. So we'll just call that Q naught. Okay. So let's see. If we had 2 point charges, we'll say Q and Q naught, separated by a certain distance R. We know that the force between these two charges should be Q naught over R squared. Now, I didn't mention this before explicitly. I think it was implied that this force is a shared quantity. Now that we've talked about what a shared quantity means, the force on Q from Q naught is going to be the exact same as the force from Q naught vice versa. The force on Q from Q naught is the same as the force on Q naught from Q. Okay, they both feel a repulsive force. So let's just write that out. Shared quantity. But what we did was we defined this new term, the electric field, which takes you from a shared quantity to a new type of quantity, which is, we don't have a word for it, but the electric field doesn't depend on both. It just depends on the charge producing the electric field. Okay. So we've claimed that charges produce electric fields. And so we go from this quantity which is shared between the two to a quantity that tells us something about only the charge that's producing the electric field, Q. Okay. We're going to do something very similar with electric potential. Okay. At this point, we know that if a charge is in an electric field, it has electric potential energy, which we call UE. Okay. UE happens to be a shared quantity, right, between the two charges, if you have two charges near each other. This is what we're going to do. We're going to define the electric potential. Okay, it's not potential energy, it's electric potential, and we're calling it V. And we're going to define it this way. We're going to say V is U over Q naught. Where U, or UE, we've been calling it, UE is the electric potential energy that Q naught has at a particular point. And remember, UE, let's say we had this same setup with Q and Q naught. Remember, UE is KQ Q naught over R. It's a shared quantity, just like force that we plugged into the definition of electric field to get KQ over R squared. So let's see what this says about point charges. Okay. So we have, let's say, let's first write electric potential around point charges. So we're going to assume that we have two charges just like in that previous picture, Q and Q naught, separated by a distance R. We want to know what is the potential, not potential energy, what is the potential at the location of Q naught. Well, we know that the electric potential is defined by this equation. And we can go a step further and plug in our equation for UE. If we have two charges separated by a distance r, then the potential energy shared between them is KQ Q naught over R. Now what happens is very nice. We have KQ Q naught over R all over Q naught. And look what happens. The Q naughts cancel. So the potential only depends on Q. This is the electric potential created by Q. What this is telling us is that not only do charges create electric fields, they create what we call potential fields. Not only do charges create E fields, they also create a field of electric potential. Okay. Now, what does this mean? What does it look like? So let's zoom in on just that one charge, little q. We know that the electric field around Q is a collection of vectors with decreasing magnitude as you get further away that are outward in all directions. Okay, this is E. But it's a vector at every single point in space around that charge. Now, what it means to have an electric potential at every point in space, or a field of electric potential, it means that there's a scalar at value at every point in space. So since you can't really, the only way to draw a scalar is with a dot. So everywhere in space, there is a scalar. Oops. And that equation, or that scalar represents electric potential, KQ over R. Whereas electric field, you have KQ over R squared, R hat. Now, what is a scalar field? A field full of scalar quantities. I mean, just a number at every point in space. So other scalar fields, other common scalar fields, other than obviously potential, the only one I can think of right off the bat is temperature. I think we mentioned this actually when we started talking about electric fields. We said that inside our classroom, or inside the room that you're in right now, there is a temperature value at every single point in space. Now, all of the temperature values probably in your room are relatively the same. The temperature doesn't vary much around a small room. But that just means you have a uniform scalar field. It's constant everywhere. So if you thought of that as electric potential, then the potential in at every spot in your room would be the same. Okay. It's not the case with point charges, right? The electric potential when you're close in is higher than the electric potential when you're further away. Another couple things, just generic stuff about electric potential. It has units that are volts. Let's see. What else should we mention about electric potential? It has units of volts. It is also related to work. You can sort of relate it to work since work is equal to minus the change in potential energy. Well, we have this equation for V is equal to U over Q. So this is actually the same equation as a change in electric potential is equal to a change in electric potential energy over Q. Okay, between 2 points. If you were to solve for delta U and throw it in here, work is equal to minus Q delta V. So you might throw this equation around occasionally. Okay, let's do some examples. So I just want to reiterate, okay, not only do charges create electric fields, around every point charge, every charged object, there is electric potential. Just numbers. Okay. And while it is slightly different, it is very intimately related to, and you can sort of think about it as electric potential energy. It's just slightly different. Okay, so it might help to summarize this. Actually, before we do that, just a quick note on voltage. We mentioned this today in lab, but a voltage is said to exist if there is a difference in potential between 2 points. Okay. Which means if you have a potential difference, mathematically you would write that as a delta V, right? Okay, so just to summarize, we have 3 new quantities that are all pretty intimately related. You have electric potential energy, which is U. You have electric potential, which is V. And we also have electric potential difference or voltage, and those are the same thing. And that is delta V. Okay. Once we start talking about circuits and leaving sort of point charges behind, we will drop the delta and just say that voltage out of a battery, for example, is V. I think we did that in lab today. But for now, let's leave delta so that we get familiar with the fact that it's a change in potential between 2 points. All right, so let's talk about some calculations with electric potential. Now, electric potential, again, is something that all charges create. So we could ask, instead of, so since we know the potential created by a single charge which is V equals KQ over R, what is the potential around, or created by rather, many charges? So something similar to what we did with electric potential energy. We asked, we have a bunch of point charges all in a close group. What is the total potential energy of the system? Something similar here. If you have, let's just do 3 point charges, Q1, Q2, and we'll do Q3 over here. Okay. Now, this is not going to be very similar to, well, it is and it isn't. We're not worried about the pairs of charges anymore. What we're looking at is, suppose we have a point that we're interested in. We want to know what the electric potential is at that point. Then what we would have to do is figure out what the electric potential is due to Q1, figure out what the electric potential is due to Q2, and the electric potential due to Q3. Okay? And then add them all up. So it looks something like this. The total electric potential at this point is equal to the electric potential just due to Q1 plus the electric potential just due to Q2 and the electric potential just due to Q3. Now these individual V's, V1, V2, and V3, can be found with KQ over R. So we'd have KQ1 over R1 plus KQ2 over R2 plus KQ3 over R3. Again, it can get tedious because there can be many terms, but you're just adding numbers because there, again, are no vectors here, which actually is one of the main reasons we're defining electric potential, because it turns out it's easier to calculate the electric potential than it is to calculate electric fields in a lot of cases. And what we'll see in a few minutes is that if we know electric potential, we can actually figure out electric fields from electric potential. Okay. So if you have any more than 3, you just keep adding for however many point charges you have. So that's one sort of calculation, and we can do an example of that in a few minutes. The only other type of calculation that we have is, what if we had a continuous charge distribution? Okay. What we do there, and it's going to be almost exactly the same as when we had continuous charge distributions with electric fields. Okay. So let's assume we have some blob of charge, Q. We want to know what is the electric field, what is the electric potential at this point? A distance, it doesn't matter what the distance is. So this is going to work the exact same way that it did with the electric field case. We're going to zoom in on a tiny little patch. That patch is going to have some size, and it's going to have some charge on it, dq. The size, depending on the geometry of the problem, if you have a rod, if you have a ring, we'll call it something different, so we don't have to worry about what that's going to be right now. And what we would do is then figure out what is the tiny electric potential, dV, associated with dq at that location. So we would need to know the distance as well. But since dq is just a tiny little patch, we can use the equation of a point charge, k dq over r. And then you integrate both sides, and you'd start out with an integral that looks like this. Now, when we do an example of this, we will again rewrite dq in terms of charge density and before we integrate and all of that good stuff. But in general, this is where you would start for any sort of continuous charge distribution. All right, let's see. Before we do an example, there's one more thing that I want to touch on, and it is the real reason why we are even worrying about computing electric potential. So why are we concerned with calculating V? Why do we even define this quantity? Are we just making things harder for ourselves? Turns out we're not. The reason that we are finding electric potential is because we can actually use it to find electric fields. Right? The whole goal of the course which I mention quite often, is to compute the E field in a variety of ways. Potential gives us an easy way to compute E. Okay. So, what I want to do for the next 5 minutes or so is figure out how is electric potential related to electric field. So we haven't seen that yet. We've just figured out how to compute electric potential. So how are V and E related? Okay. The first way that they're related is through the concept of work. So let's assume for a second that we have a charge located at point A, and it moves on some wacky path to point B. And while it does so, there's some electric field that is acting on our charge. So we have a little Q in here. The question is, let's compute the work done by the electric field on our little Q. Well, the first way that we could do it is by looking at our equation that relates potential energy to work. So work is equal to minus delta U. But we said that delta U is equal to Q delta V. Right? That's how we defined electric potential. Right? We said V is equal to U over Q. adding these deltas in actually doesn't make a difference. I can prove that to you just for, as an aside here. Okay. So delta U is equal to UB minus UA, right? Your final potential minus your initial potential. And just to indicate that those are final and initials, there, add some arrows. Well, the potential energy at point B, we can just write as VB over Q. Or, I'm sorry, I had it the other way around. Q VB. Likewise, at point A, the potential energy can be written as Q VA. Factor out a Q, VB minus VA, which is Q delta V. So we have that work is equal to minus Q delta V. Okay. Let's hold on to this for a second. Now, let's look at another way of computing work. Remember, work is also equal to the integral from A to B of F dot dr. But what would the force on Q be at any given point inside this electric field? We can calculate that because F is always going to be equal to QE. Okay, this is just the definition of electric field. So we can go ahead and plug that in. And we have work is equal to Q integral from A to B of E dot dr. So you've got two equations for work. One related to potential, one related to electric field. So now we're going to set these two equations equal to each other. And we'll have one equation that relates potential to electric field. So we have Q, is it minus Q delta V? Yes. Minus Q delta V is equal to Q, times the integral from A to B of E dot dr. Okay. Q's here are going to cancel. And since minus signs are stupid to work with, let's rewrite this delta V. We have minus VB minus VA equals the integral A to B E dot dr. So let's just take the minus sign in there and we'll just flip. It's VA minus VB is equal to the integral from A to B E dot dr. So now we've got an equation that relates these two quantities. Now I said before that the equation that relates, or the reason that we compute V is because it allows us to get electric field. And it actually is pretty easy to compute the electric field from potential. This doesn't look like it's very easy to compute electric field, right? It's in some nasty integral with a dot product, which you all, I'm sure, really love at this point. But this equation doesn't actually allow us to get electric field from potential. This, if we knew the electric field beforehand, this equation would allow us to find V. Okay, so this is going the opposite direction. If we know E, we can get V. What we want is a way of going from V to E. Okay, so that's what we're going to look at next. All right, and this is the last thing that I want to do for this lecture, and then we'll be done. We are going to revisit equipotential surfaces. So just to refresh your memory on equipotential surfaces, we looked at gravity first. We said with gravity, if you look at a contour map of, let's say, a mountain range, let's make this a little better here. Something like this. Okay. Each line represents an elevation. Lines of equal elevation. Okay. But since gravitational potential energy just equals mgh, where h is your elevation, these are also lines of equal potential energy. Hence the term equipotential lines. Equipotential lines. Okay. All right. We did the same thing for electric fields. Right, we said that if you had two plates, something like this, plus, plus, plus. In lab, it was your job to figure out where those lines of equal potential were using a voltmeter. And what you found using Excel was that those lines go straight parallel to the two plates, the charged plates. So these were lines of equal electric potential. Okay. All right. Let's look a little bit at the relationship between the electric field and these electric potential lines. I told you the answer in lab, but I want to show you now. So, on any line of equal potential, what is the work required to move a charge? So, what I'm asking here is, if we know that there's a line of equal potential right here, and I take a charge Q, and I move it along that line to another point that is still on that line, what would be the work required to do that? Take a second and think about it. But I will give you the answer. It has to do with our simple equation for how work is related to potential energy. Right? Work is equal to minus delta U. So in order for you to have to do work on an object, there's got to be some change in electric potential energy. In this case, you're on a line of equal potential energy. So from this point to this point, delta U is equal to 0. 0 joules. So in that case, the work required to move that charge from this point to this point is 0 joules.